In this video, we will be learning about calorimetry, which is a measurement of the amount of heat transferred from one substance to another substance. And oftentimes, people get heat and temperature confused. So here's a definition of heat. It's a measure of the transfer of energy from one substance to another substance because of a difference in temperature. So if we're measuring the amount of heat, we use Q to represent that heat. So Q is measured in joules, and that is the amount of heat. And Q is the letter that we use to represent that heat. So whenever we do calculations or use equations, Q will be our heat measurement. Now let's just say, for example, I wanted to know how much energy it takes to heat up a piece of aluminum. All right, I'm going to need to know a few things in order to figure that out. I'm going to need to know three things. First of all, I'm going to need to know the size or the mass of that piece of aluminum. How big is it? And we will measure mass using grams. So 500 grams of aluminum would take a lot more energy to heat than 1 gram of aluminum. So mass is very important. The mass of the object or the mass of the substance that you're heating is important, so we include that in our equation. The second thing we include is something called the specific heat capacity. Now basically what the specific heat capacity is it's a measure of how easy is it to heat up this substance. Certain substances heat up very easily, like aluminum, and some substances heat up it takes a lot more energy. It's a lot more difficult to heat certain other substances, like water, for example, has a very high specific heat capacity compared to aluminum. The last thing we need to know if we're figuring out the amount of energy it takes to heat a substance is how much we're heating it. If we heat it 100 degrees, it's going to take a lot more energy than if we only heat it 2 degrees. So the change in temperature is the third component to figuring out how much energy it would take to heat something. So we have the mass in grams, we have specific heat capacity in joules per gram degree Celsius. And by the way, the specific heat capacity is something that it's specific for each type of substance. It's not something that's universal. And then we have the change in temperature, which is measured in degrees Celsius. Now, anytime you see that delta symbol, it means the final measurement minus the initial measurement. It means we're changing the amount of something. So we're heating it or cooling it and changing its temperature. A little bit more about the specific heat capacity. The specific heat capacity we symbolize capital C for that term, and it is the amount of energy needed to raise 1 gram of that substance by 1 degree Celsius. So how many joules does it take to heat 1 gram for every degree Celsius? And the unit for that represents kind of the definition, so joules per gram degree Celsius. If you take a look at our aluminum is 0.903 joules per gram degree Celsius. That's the specific heat of aluminum. Other substances like water heat with much more energy. Much more energy is required to heat water. So water has a specific heat capacity of 4.18, and we're going to add an extra sig fig on there, 4.184 joules per gram degree Celsius. So different substances heat more easily or more with much more difficulty depending on what the substance is made of, metal versus different molecules. So let's take a look at a practice example. How much heat is required to warm 150 grams of sand from 25 degrees Celsius to 100 degrees Celsius? So to do this problem, I need to do a little bit of footwork first. I need to figure out my change in temperature. So the change in temperature is the final temperature minus the initial temperature. So I'm heating this substance, so it's getting hotter. The final temperature is 100 degrees Celsius. The initial temperature was 25 degrees Celsius. So I heated this substance by 75 degrees Celsius. So I'm going to start with my equation. Q equals M times C times delta T. Now the mass. The mass of the substance, I look at my problem here, and I have sand. The mass of the sand is 150 grams. So I'm going to put in 150 grams for my mass. Now if I look over on the chart, this table of different substances with their specific heat capacities, I can find sand at the bottom. By the way, you can feel the difference in specific heat capacity between sand and water every time you go to a beach. At night, or when it's cooler out, the water is very warm and the sand is very cool because it takes the water a long time to cool down because it has such a high specific heat capacity. The sand cools down really quickly. And during the day when it's really hot, the sand heats up very quickly. So sometimes it gets very difficult to walk on the sand. What do? You go into the water because the water takes much more energy to heat and it heats a lot more slowly. So your feet can be cooled off by the water during the day. Now, back to the problem here. We have a change in temperature of 75 degrees Celsius. I plug everything in. Now, let's take a look at the units. Degrees Celsius and grams both cancel out, giving me final units of joules, which is exactly what I want when I'm calculating an energy change. So Q should have units of joules because all of the other units cancel out. Now, when I type this into my calculator, I get 9,450 joules. That's the amount of energy that it takes to warm up 150 grams of sand from 25 degrees Celsius all the way up to 100 degrees Celsius. So we're going to take a look at another practice problem here. What is the heat change when 5 grams of aluminum cools from 232 degrees Celsius, which is the temperature inside an oven, to 21 degrees Celsius, which is the temperature of your kitchen? So basically, how much energy is being released by this aluminum when you take an aluminum pan out of the oven and put it in your kitchen? And the amount of energy that's released by the pan is equal to the amount of energy that is gained by your kitchen. So we can calculate both things here using this equation. So we have 5 grams of aluminum and it's cooling from 232 Celsius down to 21 degrees Celsius. Now we're going to do our footwork first, our pre-work on this. The change in temperature is equal to the final temperature minus the initial temperature. Now this is an object that's cooling, so the final temperature is going to be cooler than the initial temperature. So we have 21 minus 232 degrees Celsius. So we get a negative number for this change in temperature. We get negative 211 degrees Celsius for our change in temperature, which makes sense because our aluminum pan or whatever it is cooling down, so the delta T should be negative. Now we're going to plug this stuff into our equation, Q equals mc delta T. The mass is 5 grams. The specific heat capacity of aluminum is 0.903 joules per gram degree Celsius, and the change in temperature is negative 211 degrees Celsius. It cooled down. So when we multiply all of this out, we get mass times C times delta T, 5 times 0.0903 or 0.903 joules per gram degree Celsius times negative 211, and I get negative 953 joules. So what that means is the pan is losing 953 joules, and the environment, the kitchen, is gaining 953 joules. More on this on the next slide. Here we go. So when two substances of different temperatures are combined, so the pan in the kitchen or this piece of metal in the water, the thermal energy flows from the warmer one to the cooler one. And according to the law of conservation of energy, the heat lost by one is equal to the heat gained by another. So we can set up an equation here. The Q, or the heat lost, is equal to negative the Q gained by the other substance. We could break this down into individual components. So the mass times the C, the specific heat capacity, times the delta T of the substance that loses the energy is equal to negative mg, or gained, times C gained times delta T gained. Here is a final practice problem, and it's a little bit more detailed than the previous two. If we have a block of copper and we don't know the mass, it has an unknown mass, the initial temperature is 89.6 degrees Celsius, and then the copper is immersed into a beaker containing 82.4 grams of water at 20.3 degrees Celsius. When the two substances reach thermal equilibrium, meaning that they are the same temperature, the final temperature of the whole system, so the water and the copper chunk, is 26.8 degrees Celsius. What is the mass of the copper block? So what we're trying to figure out here, what we're trying to find is M sub L, or the mass of the substance that loses the energy, the mass of the substance that's cooling down, so the copper in this situation. Now we're going to go back and figure out the Q, the total amount of Q energy that's lost. So we need to take the mass times the specific heat capacity of the copper, which is 0.385 joules per gram degrees Celsius. And then we're going to multiply that by the change in temperature of the copper. Remember, the copper is cooling from 89.6 down to 26.8. So I'm going to take 26.8, the final temperature, minus the initial temperature, which is 89.6 degrees Celsius. So I plug those into my calculator, 26.8 minus 89.6, and I get negative 62.8 degrees Celsius. So this copper cooled down. So we have a negative 62.8 degrees Celsius. Now this is going to equal all of this energy that is lost by the copper is going to be gained by the water. So we have 82.4 grams of water. The water has a specific heat capacity of 4.184 joules per gram degree Celsius, and the amount of the change in temperature of the water is going from, the water is going from 20.3 degrees Celsius up to 26.8 degrees Celsius. When I submerge that hot aluminum in the water, or that hot copper, in the water heats up. And it heats up by 6.5 degrees Celsius. All of this goes in parentheses with a negative on the outside of it because we want these two components, these two sides, to be equal. So if I take my mass of the substance that loses the energy, and I take these two pieces, the 0.385 joules per gram degrees Celsius times negative 62.8 degrees Celsius, I get negative 24.178 joules per gram. The degrees Celsius cancels out right now in this kind of this work that I'm doing, kind of the intermediate, or as I solve this problem. So the Celsius has canceled out on the left-hand side, and I get, multiplying all of these things together on the right-hand side, I get negative 2,241 joules. Now on the right-hand side, grams and degrees Celsius cancel out, so I just get joules on the right-hand side. And then to solve for the mass, I take 2,241, or negative 2,241 joules, divided by negative 24.178 joules per gram. The joules cancel out, which gives me 92.7 grams. Also, the negative signs cancel out as well. So I get 92.7 grams as the mass of the copper in this problem.